everywhere on this planet. Ladies and gentlemen, the next king of pop, Aaron Carter.
Alright, hey, what's up? I'm Aaron Carter, and just to let you know, I always use a lot of math, science, and technology in my concerts and shows. That's why I want you to watch the NASA Y-Files. It's great. It makes learning math, science, and technology fun. So stay right where you are and check out the NASA Y-Files.
Hey, you hear me? Yeah, you come see our clubhouse in a tree. We are kids on a mission to educate ourselves about the NASA vision. Come explore math and science, cause that's what makes our alliance. We are the Y-Files Club. We yearn to learn and want to see everything that we can be. So come join us on our journey. Don't you touch that dial. And welcome to the NASA Y-Files.
When it comes to solving the Treehouse Detective's latest mystery, you need to answer these key questions. How does light travel? How does the problem board help the Treehouse Detectives? What are the 4 parts of a wave?
That's cool.
That's amazing.
I wish I could be Franz Ferrari.
Why?
Because then I could make that bright red sun disappear.
Look at the sunset. It's so red it looks like a ball of fire.
Yeah. Ladies and gentlemen, I'm about to perform the most amazing trick.
What's with him? I bet he thinks he's a magician.
Watch closely. Before your very own eyes, I will make this coin disappear.
Okay, Franz, I gotta see this one.
Abracadabra, make this coin disappear. Gone.
Where did it go?
It went up his sleeve.
It did not. It's magic.
Then make us disappear because that sunset is blinding.
Yeah.
But no one's here.
The magician is here.
Jacob.
I'm starting to get this magic stuff down.
Welcome to Kids Science News Network's morning show. Get out of bed! You're going to be late! I'm Ted Toon. This morning's top KSNN story, red skies, warning or delight? We go now to I Am Listening with a live report.
Thanks, Ted. I'm here with Captain Mac Arell of the cargo ship Dawn's Early Light. Now, Captain, the saying goes, red skies at night, sailor's delight. Red skies in morning, sailor take warning. Are you delighted or worried?
I just don't know. It's supposed to be one or the other. I'm so confused.
Well, Ted, it looks like we may never know. Back to you.
Thanks for that illuminating report, I Am. So far, no one has been able to explain the mystery of the red skies over the area. Stay tuned to KSNN for more information.
Last night, we noticed that the sunset was a deep, deep red.
I know. Maybe there's a fire around here, and we're seeing the reflection in the sky.
This looks like a case for us to solve.
I can see the headlines now. The Treehouse Detectives solved the case of the mysterious red light with magic.
Jacob, give it up.
Give what up?
He's up to his magic tricks.
Yeah, I saw some of them yesterday.
Where can we start our investigation?
With the NASA Y-Files investigation log sheet. It's great. You should really use it in your investigation.
Go to the NASA Y-Files website, then click on the treehouse. Then click on the tool selection.
Now click on the investigation log sheet and print it out.
Hey, there's Dr. D. Maybe he can give us a list of experts. This is all part of Science's inquiry.
Here I am.
What are you doing?
Just an experiment that didn't work very well. But I'll show you an experiment that will work. Watch this.
That's magic.
No, not magic. It's just good science. If I poke the skewer through this end, where it's not stretched very much, and take it out through the tip, where it's also not stretched, it won't burst. But if I poke it in the side like this,
it would pop.
That's because it's being stretched too tight.
That's great. Dr. D, have you noticed the red sunrises and sunsets?
Yes, I have. I just watched a report on it on KSNN.
We decided this is a case for the Treehouse Detectives.
We want to know what's making the sunrises and sunsets so red.
The treehouse detectives have solved a lot of problems. Think back, where do you usually begin?
In the treehouse?
Yes, that's correct, but it's a tool you always use in your investigations.
I know it. It's a scientific method.
Yes, again, remember, this is a tool you can use every day.
We know our problem. I wrote it down in our investigation log. Why are the sunrises and sunsets so red?
All right, you have your problem. What comes next?
Probably research, since we don't know much about the problem.
Research means asking a lot of questions, making observations, and talking to a lot of experts.
That's correct. Remember, with the scientific method, you research the problem, form a hypothesis, and then test the hypothesis. It's not always easy.
We know that for a fact.
In our past cases, we tested our hypothesis by experimenting and collecting data.
I think you're ready to tackle the sunset problem now.
Thanks, Dr. D. I'm sure we'll be back.
Let's see. What would make the sunset so red?
Red's a color.
And the sun gives the earth light. But why would the light from the sun be a deeper red now? I don't know, but I think we need to do research on light.
Yeah, because I think light has colors in it.
I'm doing an internet search on light. Maybe we can find a museum that has an exhibit on light. I'm typing the keywords science, museum, and light into the search engine. There are a lot of museums listed. Here's one in Boston. It's called the Boston Museum of Science. It looks really cool. PJ and his parents are in Boston. I'll send him an email and tell him to take a trip to the museum.
I hope he remembers to take the investigation log sheet. If you go on a field trip of your own, this is a great worksheet to take with you to record all of your information.
That's weird. When I look on top of the mural, I can't see anything. Then, when I look at the filter, I can see everything. Why is that?
It's because of polarization. Welcome to the Boston Museum of Science. My name is Michael Sheese, and I'm in charge of the museum's physical science program.
Hi, Mr. Sheese. I'm PJ. Well, you see, the treehouse detective sent me an email, and they said that coming here would be a great place to learn more about light. So here I am.
We've got a great exhibit on light and optics called The Lighthouse. What exactly would you like to know about light?
Well, I think I should understand what exactly is light.
I've got a great place to start.
Okay, great.
All light is energy. Do you know what the main source of energy is here on Earth?
The sun?
That's exactly right. The sun is a natural source of energy. Light can be either artificial or natural. What might be an example of an artificial source?
Would that be something like a light bulb?
That's right. In fact, I happen to have one right here.
Cool.
Let's go.
Okay. Is light the same whether it's artificial or natural?
All light is made up of photons.
We learned about photons in our electricity mystery.
And did you learn about atoms too?
Yes, we did. There are 3 different parts: protons, neutrons, and electrons.
That's right. The electrons that make up light are unstable, and from time to time they absorb energy. One of the ways the atom gets rid of this energy is it releases it in a bundle of light called a photon.
Are there different kinds of photons?
Yes. The amount of energy that's in the photon determines what kind of light wave is produced.
Wait a minute. Light is a wave?
That's right. In fact, I've got a demonstration of it right here. I'm going to hold on to my end of the rope, but I'd like you to take the other end of the rope. And if you can wiggle it back and forth, we can demonstrate what a light wave might look like. Light coming from the sun takes 8 minutes to reach us, and that's 98 million miles away.
Whoa, that's fast!
As you can see here, light travels in a straight line called a ray.
Yes, but then when I put the light on the prism, the light bends.
That's right. Light will travel in a straight line unless it hits something and becomes obstructed.
Oh, I think I understand.
Why don't you take some time and explore some of our other exhibits on light and optics?
Thanks. I saw some great exhibits that I want to go to.
Great.
Bye.
See ya.
Wow, this is so weird. I can't grab the spring. This is just like what I saw in the Franz Ferrari's magic show. Man! Am I seeing things? And for my final light exhibit, I can create my own picture by waving a wand.
Wow, the sunrise this morning was even redder than the one yesterday. I read PJ's investigation log online, and his notes on the Boston Science Museum are great.
Hey guys.
Hi.
You really missed out on a fantastic trip. Look what I brought back. It's called a prism.
Ooh, let me see it.
I learned at the Boston Museum of Science that light travels in waves, and it's also a ray.
But we learned in math class that a ray is a straight line. How can light travel in waves and be a straight line?
What do we know?
We know that there have been bright red sunsets and sunrises.
We know that light travels in a wave.
What do we need to know?
We need to find out how light can travel in waves and a straight line.
Where can we go?
NASA Langley Research Center is probably the best place to start.
I knew you'd say that, but it's so true. To do flight research, you have to study a lot of different things in the sky.
Hi, my name is Clayton Turner. I'm a research engineer here at NASA Langley Research Center.
Hi, I'm Kaylee. I'm Catherine. Nice to meet you. We're trying to solve a problem, and we need to know how light can travel in a wave and a straight line at the very same time.
Well, perhaps I can help. I do a lot of research with light on this laboratory.
That doesn't look like a laboratory. That looks like a plane.
Well, this is NASA Langley's 757 Ares research aircraft. Come on board.
Do you fly this plane?
No, I don't fly the plane. We use this plane to conduct research. In particular, we use light to study the atmosphere.
What's that?
This is a spectrometer. Let's go in the back and I'll tell you a little bit more about it. This is a spectrometer. It collects light and sorts it by wavelength.
Can you tell us more about light as a wave in a straight line?
Yes, light can be thought of as particles called photons that travel in a wave-like pattern.
But we also learned that light can travel in a ray, which is a straight line.
Yes, a simple model of light is called a ray or straight line. The arrow at the end of the line shows the direction that the photon is traveling in.
But what about a wave?
Light, or electromagnetic radiation, is a form of energy called radiant energy that has an electric field and a magnetic field. If you take the simple model shown on the screen and add an electric field, it would look like this.
That looks funny.
Look at the ends of the electric field.
It looks kind of like a wave, but why are the lines different heights?
First, let's look at a model of the wave.
He knows magic too.
The top of the wave is called the crest. The bottom of the wave is called a trough. The wavelength is measured from the top of one crest to the top of the next crest.
Do different wavelengths mean different things?
Yes, color is typically described by the wavelength or frequency. For visible light, violet has the shortest wavelength and red has the longest.
So what is frequency?
Frequency is the number of times the crest of the wave passes a stationary point.
I get it. So the shorter the wavelength, the more waves would pass a stationary point, and that would be high frequency.
So violet is high frequency, and red is low frequency.
Is there anything else we should know about a wave?
Yes, amplitude.
Why is this important?
The amplitude is half the distance from the crest to the trough. The higher the amplitude and frequency, the higher the energy.
Thanks for letting us go on the 757. We learned a lot.
I really hope this information helps you solve your problem.
So what's our hypothesis? I think it should be that there are low-frequency waves in the sky. That makes the sky red.
I'll write this hypothesis in our investigation log.
I guess that makes sense. I don't know what could be causing the low-frequency waves, though. Think we should do a little research. Remember, in our past cases, our hypothesis hasn't always been correct.
So what's up? Will the treehouse detectives find out what's causing the red sunrises and sunsets? Could there be something causing low-frequency waves in the sky? Stay tuned for more of The Case of the Mysterious Red Light.
The treehouse detectives still need your help. Look for answers to the following questions to solve the mystery. How does light refract and reflect? Find examples of translucent, transparent, and opaque. Why is the sky blue?
Put that spot on my clothes. Where'd it go? It disappeared.
There it is on the wall. How did it get over there?
With my mirror. When light hits the mirror, it bounces around the room.
Light can bounce? I'm confused. I thought we learned from Mr. Turner that light travels in a ray.
This isn't doing that.
We need to find out because they could be low-frequency waves bouncing around the sky.
Where should we go?
My class went on a field trip to the Jefferson Lab in Newport News, Virginia. They do a lot of research there.
Let's get up and go.
Hi, I'm Michelle Shen. Welcome to the Department of Energy's Jefferson Lab.
Hi, Dr. Shen. This is a neat-looking place. What do you do here?
Well, I'm a laser physicist. That's a scientist who studies and makes different kinds of lasers and uses them to hit different objects.
Lasers, like in Star Wars?
Well, sort of like that. So anyway, what can I help you with today?
We were using mirrors this morning and noticed a light bounced around the room. We want to know more about how light bounces.
Well, I'd be happy to answer that for you, Bianca. Light that bounces off a surface is called reflective light. The type of surface determines the kind of reflection you get.
A mirror is really shiny. Does that make a difference?
It makes a big difference. If the surface is shiny, then the image you see looks just like the object.
So a surface that is not shiny and smooth will scatter light?
That's right. You catch on really fast.
Does light only reflect?
No, light also refracts.
What does refracted mean?
Well, Bianca, I think it's easiest to show you. Okay, Bianca, we need to put on some gloves and goggles because you're going to work with some liquid nitrogen.
We use these in science.
Good. It helps to be safe when you're doing experiments.
What's that stuff bubbling?
It's liquid nitrogen. We're going to use the vapor to explore reflection and refraction. So Bianca, this is a laser and I'm going to shine it on the gelatin. But first I need to have you dim the lights. What I'm going to do now is shine it on the gelatin. Look closely and tell me what you see.
I see the light coming off into the gelatin. That must be reflection.
Right.
But the light is also being bent. Why is that?
Well, when light travels from one medium, such as air, to another medium, such as gelatin, its speed changes. And when the speed changes, the light bends, and we call that light refraction.
Does the speed of light speed up or slow down when it's going through the gelatin?
Well, because the gelatin is thicker than air, it slows down.
I wonder if magicians create some of their magic with mirrors.
This is a concave mirror. It curves inwards, and you can see that your image, if I hold it in one way, is upright, and then as I get closer, it gets inverted. It turns upside down.
That'd be an easy way to stand on your head.
It really would. This is a convex lens. You can see that the surface curves outwards, and as you look at it, you look much smaller. And another place that uses lenses and mirrors is NASA. Well, NASA needs mirrors and lenses for their big telescopes. Space telescopes like the Hubble telescope, or the Mars Global Surveyor, or the GOES weather satellites.
That's cool. Thanks, Dr. Shin. Bye.
I wonder if the illusionist, Franz Harari, uses mirrors to make things disappear.
Maybe he uses light in mirrors. Like he'd ever tell us his secrets.
I'm never telling them mine. Maybe we should go to Franz's website to find out more about him.
Oh look, he's doing a live chat. Just click here and we can talk to him.
Hi, Franz.
Oh, hey there. Who are you?
We are the Treehouse Detectives, and we wanted to know how you make things disappear.
Detectives? You're gonna love this. I'm sitting in the cockpit of NASA 747. Now check this out. This is actually the official shuttle carrier aircraft. It's what NASA uses to move the space shuttle from one city to the other when it's not in space. I mean, right now, we're parked at NASA Dryden Flight Research Center. And I was here because I was checking out this airplane they have. This is the coolest jet aircraft ever. And I'm thinking, I'd like to make it disappear.
You can do that?
Well, I'm not going to give you all my secrets, but if you want, come on out, check it out for yourself.
Yeah, right. How are we going to get to NASA Dryden?
It's easier than you think. Check out your keyboard there. You see that? There's one button you haven't used yet. Right over there, this one right here.
Wow, we really made it! I can't believe he really got us to California.
Where's Franz?
Hey kids, welcome to NASA. How was your trip?
Where is he? Look, he's up there.
Our trip was pretty wild, but I like that magic. Whoa, I really like that magic stuff.
How did you get down here?
Well, you know, at NASA, anything's possible. Now, how can I help you guys?
We're investigating a problem that deals with the properties of light.
I'm a big fan of yours, and I think you use light to help things disappear.
Well, to be honest, in my business, light is everything. Now, I'm not going to give you all my secrets, but come on, I'll show you something cool.
All right.
I'm sort of all set up to do a little demonstration here for you. Now,
Here's a little model of an SR-71 Blackbird. This is like my favorite plane. It's so cool. This plane, the real plane, can actually go from New York to Los Angeles in like an hour. It's amazing. Now you see the model, but the reason that you see this model is because light is hitting the model and then bouncing back and hitting your eyes. And your eyes are telling your brain that this little airplane is actually there. Imagine this. Imagine that we put just a reflection of my hand in there. Well, we've seen that a bunch of times. But now you add another hand, and now you go into a kind of a symmetrical world, and watch this. Your brain almost tells you the reflection of the hand is the real hand. See that? Pretty cool, huh? That's where it gets really magical. Now, I was telling you about my little model here, the SR-71. Let's see if we can't do some real magic with it. I need some magic words. You got any magic words?
Abracadabra.
Abracadabra, that'll work perfect. Watch. And the reflection becomes reality. And there's one for you, and one for you. Let's try this trick one more time, and this time you figure out if you can see how light made it all work, all right?
All right.
Come with me. I couldn't help but notice you guys both have planes, but I don't have one. But I have an idea. How would you feel if I borrowed your little model for just a moment? You cool with that? All right, tell you what, you guys stand over there. Don't take your eyes off what's about to happen over here, because that's where the real magic's about to begin, all right? We will hold on to this shot until after that SR-71 has disappeared. Gentlemen, raise the tarp. All right, check it out. Wow! That's it!
How did you do that? That was amazing. How did you do it?
How'd I do it? It's all about light.
I need to make a phone call.
Oh, sure, go for it.
Hi, Dr. D.
Oh, hi, guys.
What's all that?
Thought I might be able to help you with your light experiments. Well, where are Jacob and Bianca?
I don't know. They were supposed to meet us here.
Hello?
Hi, Dr. D. It's Bianca. We're over at NASA Dryden. We're running a little late. We'll be there soon.
Where are you?
I'll be right there. Well, you're definitely great at what you do, but we gotta get back home.
Oh, well, I have an idea. Go ahead and assume the position.
What?
Assume the position.
Oh.
Yeah, there you go. Ready? We're sending you home. And when I say go, blink. You ready? Go.
We made it.
Where's Jacob?
I don't know. Franz must have sent him back to his house.
Wow, how did you get here so fast?
Just magic, or is this an illusion?
That was quite a trick.
We're learning all about light to try and solve this red sunset problem.
Yeah, I went to the Boston Science Museum. I learned how light travels in waves and in a straight line.
And we also learned a little bit about mirrors and lenses, and about reflection and refraction.
And a little bit of magic, too. Have you learned the difference between transparent, opaque, and translucent yet?
Trans what?
Let me explain. Light can pass through a transparent object and make an object on the other side clearly visible.
You mean like a window?
Yep. Take a look at this light bulb. If I turn the crank, can you see the filament clearly?
Yes, look at that.
What else is transparent?
A car's windshield?
Exactly, until it gets all fogged up, and then it's called translucent.
Oh, so translucent means that light can get through, but not just very much.
Getting very good at this. When an object is translucent, light is diffused, and you can't see the object very clearly.
That would make it hard to drive.
Now what does opaque mean? You know what that is?
I think it means that no light can get through. When there are solid objects like rock or concrete, that's opaque.
That's correct, but it's much more interesting than that. Step over there, please. Look at this example. Here I have two sheets of light polarizing material. Can you see me clearly?
Yes, it is a little dark, but it's clear, so it's transparent.
And watch what happens when I rotate one of the two sheets.
Wow, you disappeared, just like magic.
It became opaque and went black. I think I understand translucent, transparent, and opaque now. The sky is transparent most of the time.
Clouds can make the sky opaque.
I wonder if clouds are causing the problem.
I don't think it's clouds. Well, let's go back to the treehouse and organize all this information.
Bye, Dr. D.
Bye, Dr. D. See you.
Bye.
This one is definitely transparent.
And that one's translucent. Only a little light can shine through.
That one has to be opaque. There isn't any light getting through.
Dr. D would give us an A.
On a clear night, the sky looks transparent, but why does it look translucent during the day?
Yes, I wonder why the sky is blue during the day, but red at sunrises and sunsets.
This is all so confusing. Let's go to the problem board and try to figure out what we need to learn next.
We know the sky is still a bright red.
And we know that light travels in waves and is a ray.
And now we know that light can be refracted and reflected.
Maybe if we knew what causes the color of the sky to be blue during the day, it would help us to find out why the sky is red at sunrise and sunset.
I think the night sky is transparent and the day sky is translucent. That's true. What makes the sky different?
One variable between the night sky and the sky during the day is the sun.
I think we need to learn more about the sun.
I just did an internet search and found our next expert, but it took me a while. Let's call NASA Ames in Mountain View, California. They have an expert in the sun.
Hi kids, I'm Peter Paluski at NASA Ames Research Center. I study light in the Earth's atmosphere. What can I do for you today?
We're trying to figure out a problem, and we need to know why skies are blue during the day.
Good question. Let me first talk to you about the sun. It's a white light, which means that it's really a mixture of all colors of the spectrum, from blue to red.
If the sunlight is white, then why is the sky blue?
We learned about reflection at the Jefferson Lab. Could the sky be blue because it's reflecting blue off the ocean?
No, that's a common misconception. The Earth has an atmosphere, which is made up of molecules such as oxygen and nitrogen. It's also made up of tiny little microscopic particles. And these tiny little microscopic particles in the atmosphere are called aerosols.
I don't see anything in the air.
Well, let me ask you first, what do you know about light?
We learned at the Boston Museum of Science that light is a wave and that it is made up of photons.
Occasionally, the photons will actually bounce off of the molecules and particles and go off into different directions. That's something that we call scattering. Let me show you an experiment I have set up here. This fancy instrument is something we call a sun simulator, but really it's just a lamp which sort of mimics the output of the sun. First of all, you can see the beaker here has very little light scattering out of the sides of it. Now watch what happens when I add some milk to the beaker. What does the milk represent?
The molecules and particles in the atmosphere.
Now we've got plenty of light scattered out the sides, and notice it's very bluish. When we look at the sun beam that's been transmitted through the beaker, however, that's become reddened. That's because the blue light's been removed from the beam and it's scattered out the sides.
Just like the sky looks blue, but I don't understand.
Remember we said that sunlight is a mixture of all colors. Now the blue photons will actually scatter off of the particles much more frequently than the red ones. That means that we get blue light scattered out and the red light gets transmitted through.
So why do we see red skies at night and in the morning?
Well, when the sun's near the horizon, the sun beam is traveling through a very, very thick portion of the atmosphere. That's also where most of the particles are concentrated because gravity keeps the particles near the ground.
That makes sense.
Any event that puts more particles near the horizon can make the sunset and sunrise even more red than it is usually. Now, one of those events is a pollution event. I'm not an expert in pollution, but I happen to know one. His name is Mark, and he works at the Langley Research Center. So why don't we give him a call?
So cool. Wow, looks like we found the right place. Hello, Mr. Vaughn.
Hey, guys.
Well, we need to know more about what causes air pollution.
Mostly when we think about air pollution, we think about the things that human beings put into the air. We think about the emissions from factory smokestacks. They're thinking about the exhaust from automobiles. But when we actually get down to measuring the aerosol content of the air, we find out that human beings account for only about 10% of it. The other 90% comes from Mother Nature herself.
Mother Nature? But I always thought that nature was clean and natural.
Think about a volcano going off. It's not just lava that comes out of that thing. It also spits blistering hot gases way up. And those gases react with water vapor to form little tiny sulfuric acid droplets that can hang around in the stratosphere for years. Or think about big dust storms coming across the desert.
How do you know how much dirt is in the air?
Matthew, you'd be a cloud with the squirt bottle. PJ, you are going to be a LiDAR with a laser, and I'm going to stand here, my flower, and be a dust storm.
Wow, they look like sparkles.
You bet they do. We use a very similar technique when we measure real aerosols in the atmosphere. Only then we use a machine called a LiDAR. Come on, I've got one right over here I can show you.
Wow, this is a big machine. What does it do?
What we do is fire pulses of laser light out of the laser and right to this turning mirror here. From there, they shoot straight up into the atmosphere. We shoot that beam out, and just like we saw the sparkles off of aerosols in our little experiment, we use our telescope to look at the sparkles off of real aerosols in the atmosphere.
Could the aerosols from pollution cause the sky to turn red during sunrises and sunsets?
Sure they can. Circumstances are right.
We learned from Dr. Paluski that aerosols scatter more blue photons and leave the red ones for us to see.
Oh, absolutely. If you increase the number of small particles up there, they will scatter away more blue light, and you will see more red.
Thank you, we've learned a lot.
Good.
Thanks.
Good luck on your project.
Bye.
Well, I think we need a new hypothesis.
Especially since we just learned how pollution can turn the sky red.
I mean, our hypothesis wasn't wrong, but it didn't explain where the low frequency waves came from.
A stronger hypothesis would be if the sky is red, then there's got to be pollution in it.
Yes, but the hard part is going to be to figure out where the pollution is coming from. I know we'll figure it out.
What's up? Is light being reflected or refracted? Can air pollution be causing the problem? Are there any other variables that have changed to make the sunsets and sunrises so red? If so, what could they be? Stay with us next time for the next chapter of the case of the mysterious red light. Check it out.
You're getting very close to solving the mystery. Stay sharp and look for answers to these questions. What does the electromagnetic spectrum contain? How are volcanoes different from one another? What is the Ring of Fire?
That was so neat. I love all the colors in the rainbow.
How many colors are there in a rainbow?
I don't know. Let's ask Dr. D.
How many colors do you think are in a rainbow?
Roy G. Biv.
Who?
It's a guy's name. To know the colors in a rainbow, all you have to do is know the guy's name. Roy G. Biv. That would be 7 colors.
Let's use PJ's prism from the Boston Science Museum. Look at the colors of the rainbow. Let's count them.
I see red and orange.
And there's yellow and green.
Blue is really clear, but the colors on the end are blended.
That's purple. But what's that color next to it?
People think that it's indigo, but it's really just deep blue. Scientists using advanced instruments have discovered that indigo is not really a color of the spectrum.
Wait a minute, so now it's Roy G. Biv?
I'm afraid so. But I can still help you remember the colors in their order.
I'm confused. Purple, it doesn't start with a V, so is it still purple?
Well, it's actually for violet, which is another name for purple. There's another way to make a spectrum. This is called a diffraction grating.
Grating? Is that like grating cheese? Because that hurts my knuckles.
Oh, nothing like that. Here, put on these glasses with diffraction gratings. Look at that bright light source up there. Tell me what you see.
Wow. It's the same rainbow of color as we saw before. But the rainbows are everywhere.
Let's try something a little different. This is called a spectrum tube, and it's filled with helium gas. What do you see?
It's really different. All the colors aren't there. Only some of them.
Well, the diffraction grating separates the colors just like the prism does. But the gases in the tube don't produce a complete rainbow of colors. What property of light allows the diffraction gratings in the prisms to separate the colors?
I don't know.
I think it's wavelengths. Mr. Turner at NASA told us that different colors, like blue and red, have different wavelengths.
That's right. They are two of the colors of the visible spectrum. You might want to learn more about the visible spectrum. I know a NASA Langley researcher, Doreen Neal. She's going to be over at the Virginia Children's Museum.
That sounds like our next stop.
Look, she's blowing bubbles.
That's so neat. Are you Mrs. Neal?
Yes, I am, and you must be the treehouse detectives.
Yes, we are. Wow, look at these bubbles. It looks like a rainbow. You were just talking about the colors in a rainbow.
How can I help you?
We need to know more about the visible spectrum.
Tell me what you've learned so far.
Waves have different frequencies.
And different frequencies mean different colors.
The order of the waves and the frequencies is called the electromagnetic spectrum. The part that our eyes can see is only a very small part of the electromagnetic spectrum, and that's the part we call visible spectrum.
That makes sense. Well, do the other parts of the spectrum do anything?
Oh yes, televisions and radios and microwaves and cell phones all work on the electromagnetic spectrum.
So tell us more about the visible spectrum.
The visible spectrum consists of all the colors our eyes can see.
Like orange, red, and yellow.
And green, blue, and violet.
That's right. Take a look at this color wheel. We can mix those colors to make all the colors our eyes can see. If we mix all the colors of white, we get white light.
How can we see the colors in white light?
We use a spectrometer to pick out the different frequencies.
Mr. Turner showed us what it is.
Let me show you something. When you mix the 3 primary colors of pigment, you get black because pigment absorbs all the light that hits it.
That's what the pigment is. But with light, is it different?
Yes, it is. The primary colors of light are red, green, and blue. And when you mix those 3, you get white light. I hope you learned a lot about the electromagnetic spectrum today. The museum has a room full of light and color that tracks your motions. I think you might want to check it out.
Let's go. Thanks, Miss Neal.
Bye.
What are you doing?
I'm doing an experiment with colored lights. I wrapped each light with colored paper and foil.
Okay.
There's red, green, and blue.
Why do you use the foil?
The foil makes the light shine in one direction. What do you think would happen if I placed all the colors of light together?
I guess you'd have a bunch of mixed up colors.
Watch. Here, hold that. Let me hold that. Now we're gonna shine this light on this board. Watch what happens. It makes a white light.
That's right. White light does make all the colors of the rainbow.
I'm Ted Toon with this KSNN special report. Mount Luminous, the active volcano on the western Pacific island of Fugu-Puku, has erupted yet again just this morning. We flew our reporter, I Am, listening to the scene, and she brings us this live report. I Am?
Thanks, Ted. Mount Luminous is really blowing its top.
I Am. Can you tell if there are rivers of gushing red-hot lava or giant flaming boulders crashing down from out of the sky?
I can't see a darn thing. We're out of here.
Well, there you have it. I'm Ted Toon saying that's all there is for today. Join us tomorrow when we'll be sending I Am Listening out to find a really good volcano with lava and flaming boulders and stuff.
I got it! Volcanoes erupt lava.
What are you talking about? KSNN is on the scene of an active volcano.
Lava's red.
So maybe the red lava is reflecting into the sky. Oh yeah, we learned about reflection from the Jefferson Lab.
Maybe we have a new hypothesis. If the volcano erupts red lava, then the sky may be red due to reflection.
I think we need to learn more about volcanoes.
I have to go study for a test. See you later. Bye.
All right, bye, PJ. Good luck, man.
All right, thanks.
I have this book about volcanoes. Let's look up Mount Luminous.
Here's Mount Luminous. It says it's located in the Pacific Ocean near Japan. That book says something about it being in the Ring of Fire.
I have that book.
The Ring of Fire?
If there's a ring of fire in the ocean, that could be why the sky is red.
Let's look at the globe. Here we are, and here's the Pacific Ocean.
How far is it from us?
Well, my social studies teacher said that all globes have a scale. Here it is. It says 1 centimeter is equal to 418 kilometers.
So we need to measure how far Virginia is from Mount Luminous.
Okay, let's see. That would be 27 centimeters.
I'll do the math. 1 centimeter equals 418 kilometers. Multiply that by 27 centimeters. That's about 11,286 kilometers. And there's about 1.6 kilometers in a mile, so that's about 7,000 miles.
But I don't think a reflection of red lava could be seen 7,000 miles away.
As scientists, we need to do a little more research and experimentation before we jump to any conclusions.
Dr. Paluski said that volcanoes can put out a lot of pollution in the air. Maybe pollution is causing the sunrises and sunsets to be so red.
I don't think so. 7,000 miles is a long way to travel, even for pollution. But you never know. Different types of volcanoes could cause different types of pollution.
So what do we do next?
I think we should see if anyone in the NASA Y-Files Kids Club has done any research on volcanoes.
Hi, Kaylee.
Hi, Kaylee.
Hi, Kaylee.
I knew I could help you guys out. I'll send the question to all our club members. Good, because I have to run.
Bye. I wonder what makes volcanoes erupt.
Is it like an earthquake?
I don't know, but I don't want to be around for either.
Hey look, I'm getting a response from Mr. Thomas's class at Burbank Elementary in Hampton, Virginia. They've been studying volcanoes and have even made some models. Let's dial them up to see if we can do a teleconference to find out how much they know about volcanoes.
Hi, my name is Robert Bryan, a 5th grade student in Mr. Thomas's class.
What is your project?
Well, we have been studying volcanoes and we have found out that there are 3 basic types of volcanoes.
What are they?
Let me show you some of the models that we've made then. This one is a model of a composite volcano. Its eruptions vary between quiet and violent ones. When the volcano has a violent one, it throws out ash and dust, creating a tephra layer.
Wow, that's cool. What are the quiet eruptions like?
That is when the volcano erupts lava like this.
Wow, that's cool. What are the other 2 types?
Another volcano is a cinder cone volcano. This volcano only erupts ash and dust like this. And there is a shield volcano.
Shield? You mean like what knights use to defend themselves?
Well, sort of. Take a look at our model. As you can see, the lava flows differently. It forms very flat layers, and these layers have very broad and gently sloping sides.
That's interesting. We learned a lot. Thanks for your help.
Bye from the NASA Wi-Fi's Kids Club in Hampton, Virginia.
See you later. We should build a volcano. That looks like fun.
Let's do a little research. Let's see what Dr. Textbook has to say about volcanoes.
And now, the history of volcanoes with Dr. Textbook.
Hello. Did you know that the word volcano comes from the Roman god of fire, Vulcan? And that the early Hawaiians told legends of their goddess of fire, Pele. In the year 79 AD, the Romans were the first ones to write an eyewitness account of an actual volcanic eruption. Falling ash spewed out of Mount Vesuvius, and the ash and the mud flows combined to bury the nearby city of Pompeii, thus killing about 2,000 people. 2,000 years later, archaeologists actually unearthed this ancient city of Pompeii. In April 1902, Mount Pele, not related to the Hawaiian goddess of fire, in the Caribbean Sea exploded, killing 28,000 residents in just seconds in the little town of St. Pierre. Closer to home in 1980, the sleeping giant Mount St. Helens erupted to become the most destructive volcano in U.S. history. The eruption had the force of 10 million tons of dynamite and shook the Cascade Mountain Range in Oregon and the state of Washington. So, in honor of all the gods of fire, I will attempt to find out what really makes a volcano come alive. Not a very good idea.
See, Dr. Textbook? He's so funny. Let's research Mount Luminous.
I saw an article about Mount Luminous in the paper today. Maybe it'll have some information for us.
It said that Mount Luminous was a cinder cone, and that its first eruption was a month ago.
Then Mount Luminous can't be the problem, because why would all of a sudden the skies be a deep red if it erupted a month ago?
I don't know, but I think we need to know more about volcanoes. Solving problems is hard work. My mom has to go to California on business, to the NASA Dryden Research Center and the Jet Propulsion Laboratory. Maybe we should go with her.
Okay, let's see if we can go.
Hi, you must be the treehouse detectives.
And you are Dr. Pieri?
Yeah, afraid so.
What's that plane behind you?
I've never seen anything like that before.
Well, it's an ER-2. It's a NASA research aircraft used at high altitude.
What kind of research does NASA do with this plane?
Well, this plane has high-powered cameras, and they can see a wide variety of phenomena, including hurricanes, volcanoes, earthquakes, and they can also monitor ozone.
You mean you actually fly into a volcano when it's erupting?
Oh no, it would do a lot of damage to an airplane like this.
But how can this cause damage?
Well, this isn't so much the problem. This lava rock gets ground up into fine particulate material like this. This is volcanic ash. This is the problem.
That's really light. Where are most of the volcanoes located?
There are active volcanoes in every ocean basin and almost every continent in the world. Most volcanoes are underwater and form along ridges as ocean basins spread away from them. Sometimes volcanoes form in the middle of continents and ocean basins as hotspots heat up plates.
Plates?
The Earth's crust is actually broken into pieces that we call plates. fact, another place where volcanoes form is where one plate goes underneath another plate, and that happens in the Pacific Ocean.
Are you talking about the Ring of Fire?
The Ring of Fire is a ring of volcanoes that surround the Pacific Ocean where the continents meet the ocean basin.
We learned that Mount Luminous is a cinder cone. Could you tell us more about cinder cones?
Well, sure. For instance, when cinder cones form, the magma is so sticky that the gas stays trapped inside it until the pressure builds so much that it just literally explodes. And when it explodes, it forms lots of pyroclastic material, which is really sharp.
Maybe we're getting a little closer.
Thanks, Dr. Peary. We learned so much about volcanoes.
Well, I hope this information gives you your answer.
Thank you so much.
Good luck.
Bye.
Bye-bye.
We know Mount Luminous is a cinder cone, and that means it doesn't even have lava.
That means our hypothesis is wrong.
But I don't think we have enough information yet to change our hypothesis. Let's go do some more research and experimentation.
Let's get back to the treehouse.
What's up? Could the volcano be causing the red sky? Could it be that all colors other than red are being absorbed by something? Don't miss the exciting conclusion of The Case of the Mysterious Red Light.
You're very close now. Answer these questions and you will solve the Treehouse Detective's latest mystery. What do researchers do at the NASA cave? What are two things that affect how far wind can carry particles? How does the jet stream help the Treehouse Detectives solve their problem?
What are you doing? Magic?
No, this is actually a science experiment. I punched a hole in this cup and poured water in.
What happens?
Turn the lights down and watch this.
Wow, that looks like a stream of light. The light is bending, just like the experiment Dr. Shin told us at the Jefferson Lab.
It's neat, but we still need to figure out why the sunrises and sunsets are so red.
I think pollution could be the cause.
But what's making the pollution? I don't think it's the volcanoes, because they're too far away.
Maybe wind's blowing it our way.
Yeah, right. I don't think the wind can blow things this far.
Not unless it had a lot of hot air, unlike someone we know.
I know you're not talking about me. I'll go over to the problem board and try to figure out what we need to do next.
We know the sky is still red.
We know that light travels in waves, and that it's also a ray. And the light we see is only a small part of the spectrum.
And we also know that light reflects and refracts.
Pollution can cause red skies.
Volcanoes cause some air pollution when they erupt dust and ash.
We need to know how far ash can travel through the air and if it can travel long distances. But how do we find out?
We need someone who knows a lot about wind.
Wind has to do with weather. I'm sure NASA has a weather expert. Let's go to the NASA Langley website.
Wow, look. NASA has a really cool place called the cave.
It's a computer system that we can use to look at weather in 3D.
I'll go over there. This must be the cave.
Hi, I'm Dr. Jennifer Olson.
I'm one of the Treehouse Detectives. We're trying to learn more about wind. We want to know if volcanic ash can blow all the way from the Pacific Ocean to Virginia.
I'm looking at some data in the cave right now. Would you like to step in with me and take a look?
I've heard of the cave. Sure, let's go.
First, you'll need to take off your shoes and put on the glasses.
Wow, this is neat.
We're looking at wind vectors over the Pacific Ocean and the U.S.
What's a wind vector?
Do you see the yellow arrows?
Yeah, lots of them.
Those are wind vectors. They show which direction the wind is blowing. Their size tells you how fast the wind is blowing. The longer the arrow is, the faster the wind speed is.
What about the wind vectors way up there?
These vectors are up at 12 miles over the Earth's surface. That's well above the weather.
It looks like all those arrows are pointing in the same direction. Is that normal for high altitudes?
Yes, it is. Notice that these arrows are mostly pointing from the west toward the east. That's a zonal direction in the global wind pattern.
How fast are they blowing?
At 12 miles up, most wind speeds are between 40 and 50 miles per hour. At these altitudes, there's also something that we call a jet stream.
Oh, you mean the white stuff that comes out the back of a jet we see?
Good guess, but the jet stream is a river of very fast-flowing air where speeds can reach several hundred miles per hour. That's as fast as a major tornado. Let's step outside and go to my computer lab.
Okay.
So what's the second thing that affects how far wind can transport particles?
It's the lifetime of a particle. Scientists have a tremendous amount of data available to them to study things like lifetimes of gases and particles, and much of that data is stored here at the Atmospheric Science Data Center.
I didn't know particles had a life.
Yes, lifetime refers to how long the particle stays in the atmosphere. For a particle near the surface, ash and dust will be rained out of the atmosphere within a matter of days.
So volcanic ash would not have a very long lifetime?
Not necessarily. If the ash were injected up in the atmosphere, near the stratosphere, its lifetime could be very long, in the order of weeks or months.
Would zonal winds then be able to carry the ash to Virginia?
Yes, it could. If a volcano injected particles into the stratosphere, it could be transported for very long distances by the very fast wind speeds of the jet stream.
Yeah, but the Pacific Ocean is so far away. That would take forever.
Let's do a quick calculation. It's about 7,000 miles from here to Mount Luminous. If we take a typical atmospheric wind speed of about 40 miles per hour, what do you get?
175 hours.
175 hours to transport the dust to Virginia. That's about a week. In fact, the dust plume could be transported completely around the globe in about a month.
The sky is so deep red. Is there anything about this eruption that is different?
Yes, there is. I read that this volcano also injected a lot of sulfur dioxide and water vapor into the stratosphere. These two gases react together to form tiny sulfuric acid particles.
We learned from Dr. Paluski that particles scatter the blue light.
That's right, and these particles are small enough that they act with the molecules in the atmosphere to scatter even more of the blue light from the sun's rays.
Thanks, Dr. Olson.
Sure.
I think we now have a new hypothesis. Here it is. If the zonal winds brought the volcanic ash to this area, we would have deep red sunsets and sunrises. Smart thinking, huh?
Matt said the cave was really cool. I wish you could have one here in the treehouse. I think that would be a little too high-tech, even for our treehouse.
You know what, guys? I've been thinking. Our hypothesis is incorrect.
Why?
Well, you remember when Dr. Olson told us that the zonal winds would bring the ash and dust to our area in about 7 days?
Yes.
Well, the really red sunsets and sunrises came only 3 days after Mount Luminous erupted.
So it couldn't be from the volcano because it happened too soon. But guys, you're forgetting. Dr. Olson also told us about jet streams and how they travel really fast. Couldn't the ash and dust have gotten here by the jet stream?
I think we need to find out more about jet streams.
Here comes Bianca.
Here comes Bianca.
Are you guys talking about jet streams?
Yes.
The weatherman from Wavy TV Tent came to our school last week. He said if we had any questions to contact him. I'll email him and see if we can meet him.
Thanks for seeing us, Mr. Eco. We need to learn more about a jet stream.
Sure, I can show you a jet stream.
You have one here?
Only on a screen. What do you guys know about jet streams?
We know that a jet stream is like a river of wind, way up high in the atmosphere.
And that they can travel up to a few hundred miles per hour.
That's great.
Is the jet stream always in the same place?
No, let me show you. Actually, guys, there are multiple jet streams. Let's take a look at a couple of them. We have what we call the northern jet, and that is outlined in the blue. That's responsible for a lot of the cold air that comes down to the east coast. And then we have what we call the subtropical jet. That is outlined in the red right here, and that's responsible for bringing in a lot of warm, moist air for the east coast.
We need to know if the jet stream was passing over our area the week that Mount Luminous erupted.
Sure, let's go look at the data. Actually, look, over the past 5 to 7 days, notice how the jet stream just goes further and further south. And what that does is it brings in all types of systems, and it's basically just below us, which lets everything drain down into our region. So you can see as the jet stream goes further south, all of the clouds and all the debris comes right down on top of us.
That has to be it then. If the jet stream traveled at 100 miles per hour and Mount Luminous is 7,000 miles away, then it would take 70 hours for the ash to reach our area.
With 24 hours in a day, 3 days would be 72 hours. That means that the jet stream could cause the sunrises and sunsets to be red.
I think you guys have solved the mystery.
Thanks, Mr. Eco. We really appreciate your help.
Anytime for the Treehouse Detectives.
I'm so glad that we finally solved our mystery.
But I still think there's one last thing we need to do. Let's email our Kids Club members and ask them if they've been seeing redder sunrises and sunsets.
That's a good idea. That way we'll know it's not just happening in our area.
Great. Also ask them when they first noticed the change.
Okay.
We're getting a lot of emails from all over the U.S.
A lot of our kids club members are saying that they are seeing redder sunrises and sunsets.
Let's organize the emails by states and see when everyone first saw the unusual skies.
Wow, there's a pattern with the states to the west coast. This email says they saw redder skies only 2 days after Mount Luminous erupted.
The center of the U.S. saw the unusual skies about 3 days after the eruption.
Except for the school in Dallas. Their email says they saw the redder skies just 2 days after the eruption. That's strange.
Well, remember, the jet stream did travel down into their area before it came up to us in Virginia.
You're right. I think that these emails remove all doubt that it was the eruption of Mount Luminous that caused the unusual red sunrises and sunsets. Hi, Dr. D.
Hi. Did you find the solution to your red sky problem yet?
We're pretty sure that we have.
And we did it together with the help of the scientific method. And we learned a lot about light along the way.
We learned the way light travels.
We learned a lot about frequency and wavelengths. Our first hypothesis was that there was a lot of low-frequency waves in the sky.
There was really nothing wrong with our statement. It just didn't explain why the sky was red.
At first, we thought that the explanation might be that light was bouncing around in the sky, but that was just a wild guess.
You then told us about transparent, translucent, and opaque. We thought that clouds might be the solution.
And then we thought about pollution. But what could be causing the pollution? Then we really got sidetracked. We heard a report about a volcano called Mount Luminous that was erupting. We decided that the red could somehow be connected to the red lava.
But we weren't listening to the report very carefully because it clearly stated that there was dust everywhere.
And then we missed the big clue. I mean, we thought that since the volcano was so far away that it had nothing to do with our problem.
Even though our idea about volcanoes was way off, we decided to study them.
Then we were taught about volcanic ash and how it can stay in the air for months at a time and travel thousands of miles. And we began to get back in the right direction.
So we didn't give up. We went back to our hypothesis of pollution and tried to see if it was the volcano that was giving off pollution or aerosols.
We investigated wind and wind patterns and found that aerosols can be transported long distances.
We learned that the higher up in the atmosphere aerosols are, the longer they can stay up there.
Most importantly, we learned from Dr. Olson that it was possible for the aerosols to be scattered from the volcano all the way to Virginia, about 7,000 miles away.
And don't forget, the jet stream helped to draw the aerosols to us even quicker.
And the fact that Mount Luminous gave off a sulfur dioxide gas also helped explain why the sunrises and sunsets were such a deep red.
That's great. You kept on track, researched carefully, kept an open mind, revised your hypothesis, and finally came up with a possible explanation.
It was fun and a lot of hard work. There just wasn't some magical solution, that's for sure.
It was a lot of hard work, but I believe you finally have come up with the most likely solution to the red sky problem. Congratulations.
Thank you. And now, for my final magic act, I'm going to make us all disappear.
Are you still at that? Give it up.
Please.
Abracadabra, send them back to their home. Hey, I think I did it. This is great.
Jacob, we're still here. You made us disappear, but we're still stuck in the treehouse.
Try it again, please.
Psst, come here. Is this magic or just an illusion? See you next time.
And we can start collecting here too, okay?
Yes, look at that.
Okay, guys, ready?
I didn't mess it up earlier. I don't know why I'm not getting it up.
Yeah, 6. Oh, yeah.
All right, bye, BJ. Good luck, man.
All right, thanks.
Don't laugh at me.
Couldn't you hold it or something?
I was holding it the whole time I was talking.
All right, all right.
Let's see what Dr.
Dr. D. Do I have to dial
Matthew on it. Ready? You ready to say anything after?
You took this picture from my dad. I want you to sign me your shirt.
Okay, Carolyn, get over here and get a picture taken. So you want me to be like holding it on the phone?
All right, all right.
The NASA Y-Files is made possible through the generous support of Busch Gardens, SeaWorld, and NASA Langley Research Center's Aerospace Vehicle Systems Technology Office.